Welcome to day 29 of our STL course. Today we are going to explore two advanced but essential concepts in the standard template library, function objects and predicates. These powerful tools will allow you to have finer control over STL algorithms, making your code more efficient and flexible. By the end of this session, you will learn how to define custom function objects, also known as functors, how to use predicates for algorithm customization, and the benefits they bring to your programming toolkit. Here are the objectives we will cover in today's session. We will start by defining function objects and exploring their syntax. Next, we will delve into the powerful built-in function objects that come with the functional header in C++. After that, we will focus on creating custom functors both with and without state so you can define your own logic in algorithms. We will also explain how function objects differ from function pointers and lambdas and when it's best to use each of them. Lastly, we will explore how predicates are used in STL algorithms to filter, compare, and transform data. Let's begin by understanding what a function object is. A function object or functor is simply an object of a class or struct that overloads the operator. This gives the object the ability to behave like a function, making it callable with the bracket syntax. Unlike regular functions, function objects can store state and contain multiple methods. This compatibility gives them a distinct advantage, especially when you need to encapsulate behavior with internal state. For example, the square struct you see on this slide overloads operator to compute the square of an integer, which means it can be used as a callable function in your program. So why would you use function objects in your C++ code? The primary reasons are flexibility, reusability, and performance. Functors can store state. This means they can keep track of data across multiple calls, unlike regular functions. For example, you can create a functor that counts how many elements satisfy a certain condition. Functors are reusable, which means once you define them, you can use them across various algorithms. Another important point is that functors are more optimized by the compiler, especially when used in STL algorithms, leading to better performance. Overall, functors are more object-oriented way to introduce function-like behavior into your code. The C++ standard library provides a variety of built-in function objects in the functional header, and these can be used in your algorithms immediately. Examples include plus, minus, greater, less, and more. These are template-based, meaning you can use them with any data type. For instance, if you want to sort a collection of descending order, instead of writing your own comparison function, you can simply use greater int. These built-in function objects are convenient and they reduce the need to write custom functors for common operations. This gives you more readable and concise code. While built-in function objects are useful, there are times when you need more control over the logic. This is where custom functors come in. A custom functor allows you to define your own behavior for specific tasks. For instance, here we have created a functor called isEven, which checks if a number is even by overloading operator. The logic is simple. It returns true if the number is divisible by 2 and false otherwise. You can then pass this functor into STL algorithms like countif, which counts how many elements in a container satisfy the condition defined by your functor. Custom functors give you the power to tailor algorithms to your specific needs. One of the powerful features of functors is that they can hold state. Unlike regular functions or lambdas that cannot store any data outside of their execution, functors can maintain internal data across multiple invocations. For example, in the counter functor, we track how many times the functor has been called by maintaining a count variable. When applied in an algorithm such as countif, it increments the count each time it is invoked. Stateful functors are especially useful when you need to maintain contextual information during algorithm execution or apply complex logic repeatedly across elements. Now let's talk about predicates. A predicate is simply a callable object, whether a function, lambda, or functor, that returns a Boolean value. Predicates are commonly used in STL algorithms where they help determine whether certain conditions are met. There are two types of predicates, unary and binary. A unary predicate takes a single argument and returns a Boolean, while a binary predicate takes two arguments and returns a boolean. Predicates are central to STL algorithms like COUNTIF, FINDIF, and REMOVEIF, where they define the condition or logic for comparison and filtering. Here's a practical example of a predicate in action. We use a lambda expression with REMOVEIF to filter out all negative numbers from a vector. The lambda acts as a unary predicate, returning true if a number is negative and false otherwise. REMOVEIF will then remove all the elements that satisfy this condition. This is a great example of how predicates give you the flexibility to easily customize STL algorithms with just a simple callable. Whether using function, objects, lambdas, or function pointers, predicates make algorithms dynamic and adaptable. It's important to distinguish between functors, function pointers, and lambdas. Each of these has unique features and advantages. Functors, as we have discussed, are objects that can store state and offer reusable logic. Function pointers are more lightweight and concise, but they cannot capture state or store data. Lambdas, on the other hand, are anonymous functions that can capture variables from the surrounding scope. The key difference between functors and lambdas is that functors are more reusable since they are full-fledged classes. Function pointers are typically used when you need to pass around simple function references. Knowing the differences helps us decide which to use in various situations. Now let's look at the real-world use case of functors and predicates. Functors and predicates are widely used in STL algorithms like sort, findIf, COUNTIF, REMOVEIF, and transform. For example, you can use a custom comparator in sort to order functions to order elements in a specific way, or use COUNTIF with a predicate to count how many numbers in a vector are greater than a particular value. By leveraging the power of function objects and predicates, you can write more expressive, efficient code. Functors and predicates are incredibly versatile tools that let us embed complex logic directly into our algorithms. It's time for some hands-on practice. First, try writing a functor called isPrime that checks if a number is prime. Next, create a functor named rangeChecker that accepts a minimum and maximum value and checks if a number falls within that range. Finally, use a custom functor to sort a collection and count how many comparisons it performs. These activities will help you solidify your understanding of functors and predicates and how they can be used to optimize your code. To summarize, function objects or functors are classes that overload the operator and behave like functions. They can hold state and be reused across various algorithms, offering more flexibility than traditional functions. STL provides many built-in function objects in the functional header for common tasks. Predicates are just callable objects that return a Boolean value and are heavily used in filtering and searching algorithms. Understanding how and when to use functors and predicates will make you a more effective C++ programmer, allowing you to harness the full power of the STL. Before we finish, let's do a quick review. First, what is a functor and how does it differ from a regular function? Second, which STL header provides the built-in function objects like plus, minus, and greater? And third, can you write a functor that checks if a number is divisible by 3? Take a moment to answer these questions and reinforce what you have learned today. Welcome to day 30 of our STL template library course. Today we will explore 4 powerful and incredibly useful utilities in C++: pair, tuple, array, and bit set. These containers are essential for simplifying complex data structures and improving both the readability and efficiency of our code. Whether we are grouping values, working with fixed size arrays, or manipulating bits, these STL utilities will help us write more expressive, efficient, and maintainable code. Why should we use these STL utilities in our code? Well, STL containers help simplify the complexity of our programs. They reduce competitive grouping, repetitive coding, enhance readability, and provide clear, high-level abstractions for tasks like grouping values or manipulating data at the bit level. By leveraging pair, tuple, array, and bit set, you make your code easier to understand, maintain, and optimize. These utilities are not only vital for real-world applications, but also widely used in competitive programming, where space and time efficiency are critical. Let's start with pair. A pair is a simple yet incredibly useful container that can hold two values of possibly different types. It's a It is defined in the utility header, and its primary use is to store two related pieces of data. For example, you might use a pair to represent a coordinate, a key value pair in a map, or even return two values from a function. You can easily access the two values pair in a pair using dot first and dot second. This makes it a great tool for quick, compact data storage. Moving on to more advanced pair usage. While pairs are commonly initialized directly, you can also use makePair for more clarity and automatic type detection. This is particularly useful when the types of the elements are not explicitly obvious. Pair also supports comparison operators, allowing us to easily compare pairs based on their first and second elements. You can even nest pairs to create more complex structures such as multi-dimensional keys for sorting or searching. Let's consider an example where we compare two pairs and check if one is greater than the other. Next, let's dive into tuple. Unlike pair, which can only hold two values, a tuple can hold any number of values, potentially of different types. This makes it perfect for situations where you need to group multiple values together. For example, you might want to return a student's ID, name, and grade from a function. The beauty of tuples is that they allow you to store heterogeneous data in a single object. You can access the tuple elements using std::get, or if you are using C++17 or later, you can use structured bindings for a more intuitive and readable approach. Tuples come with some incredibly useful utilities. For example, std::tie allows us to unpack a tuple into individual variables, which can be very handy when dealing with function returns or complex data structures. If you don't care about certain values in a tuple, you can use std::ignore to skip them. Additionally, std::tuple_cat lets us concatenate multiple tuples into one, which is useful for combining different sets of data into a single entity. Now let's talk about std::array, which is a safer and more powerful alternative to traditional C-style arrays. Defined in the array header, std::array has a fixed size that is known at compile time. This gives us the safety of bounds checking when accessing elements, and it integrates smoothly with STL algorithms like std::sort, std::file, and std::for each. Unlike a regular array, you can directly use these algorithms with std::array, which makes it a much more modern and reliable choice for fixed size collections. With std::array, you gain access to several useful methods. For example, .size gives you the number of elements in the array, and .add provides bounds check access to elements. The .front and .break methods allow you to access the first and last elements respectively. You can also use .fill to set all elements of the array to a specific value. For instance, you could fill an array with zeros using .fill0 and access any element using .add2, all while avoiding common array related pitfalls such as out of bounds access. Finally, let's take a look at std::bitset. Defined in the bitset header, std::bitset is a fixed size sequence of bits. It is perfect for situations where you need to perform binary operations such as bit masking, cryptography, or low-level data processing. With std::bitset, you can represent binary data cleanly and efficiently. For example, you can create a bitset to store a binary value like 10101100 and then use the .count method to count the number of bits that are set to 1. This makes it an ideal container for handling bit level manipulation. std::bitset comes with a variety of methods for manipulating bits. For example, .set lets us set specific bits to 1, while .reset sets bits to 0. Flip inverts the current state of the bits, and .tests checks whether a bit at a specific position is set. Additionally, dot count counts how many bits are set to 1, and methods like dot to string help us to convert a bit set back into a string for easy display or debugging. These methods make bit set incredibly versatile for bit level tasks. Let's summarize the key differences between these containers in a comparison table. Pair is ideal for storing two related values such as key value pair or a coordinate. Tuple, on the other hand, is perfect for grouping multiple heterogeneous values together. Array is a safer, more efficient alternative to traditional arrays, while bitset is specialized for efficient bit level operations. Understanding when to use each of these containers is crucial for writing efficient and maintainable C++ code. To solidify today's lessons, here are a few practice problems. Try using pair to represent the coordinates or graph edges. Use tuple to return multiple values from a function or to represent complex data. Replace old C-style arrays with std::: array to take advantage of its safety features, and finally explore solving problems with std::: bit set, such as checking subsets or performing bit manipulation. To wrap up day 30, we have covered a variety of STL utilities that will make your coding more efficient and readable. std::: pair and std::: tuple allow us to group related values, while std::: array provides a modern, safer alternative to traditional arrays. std::: bit set offers powerful bit manipulation capabilities. Mastering these containers will give us the tools to write clean, efficient code, whether we are working on real-world applications or preparing for competitive programming challenges. Welcome to day 31 of our STL journey. Today we are going to dive deep into three powerful C++ 17 features: optional, variant, and any. These features help us write safer, more readable code when we need to handle optional values, multiple possible types, or dynamic typing. By the end of today's session, you will understand when and how to use these types in your C++ code. Let's get started. In traditional C++ programming, we often resort to using magic values like -1 or null ptr to signal missing or invalid data. While this can work, it's error prone and not very expressive. Instead, modern C++ gives us with three tools: optional, variant, and any. These tools allow us to communicate our intentions clearly, making our code easier to read and maintain. They also help us avoid dangerous pitfalls like dereferencing null pointers or dealing with hard-to-crack magic numbers. Today we will explore how these wrappers make your life as a C++ developer much easier. Let's start with std::: optional. An optional is a type that might or might not contain a value. It's like a box that could either be filled with something or be empty. For example, imagine a database query where the result could be absent. Instead of using -1 or null ptr, you can return an optional int to indicate that a value may or may not be present. To check if the value exists, you can use .hasValue or just cast it to bool. To retrieve the value, you can use .value, but remember, you should first check if it exists. If it's empty and you call .value, it throws std::: bad optional access, so make sure to handle that properly. While optional is powerful, there are best practices and pitfalls to keep in mind. Always check before accessing the value. You can do this by using .hasValue or by using the save.value or method that gives us a default value if it's empty. Avoid using optional with references. This is a tricky scenario that can lead to undefined behavior. Don't forget, accessing .value on an empty optional can cause runtime errors, so be sure to use it with caution. Now let's move on to std::: variant. Think of a variant as a type-safe union. Unlike traditional unions, which allow you to store one type of data but require you to manually manage the type you are storing, variant ensures that you can only access the value in a way that's safe for its current type. For example, std::: variant int, float, string can store either an int a float, or string. But the key difference is the type is known at compile time, so you don't need to worry about memory issues or undefined behavior that can occur with traditional unions. To access the value inside, you can use getT or more commonly use visit to apply a function or lambda to the stored value, no matter what its type is. With std::visit, we bring the visitor pattern into our C++ code. This function takes a lambda or function and applies it to the type inside a variant. For instance, you could apply a lambda to process the stored int, float, or string depending on the type of the value currently held by the variant. This is extremely powerful because you can easily handle multiple types without manually checking each one, making your code cleaner, more maintainable, and easier to extend. Next up is std::any. Any allows us to store any copyable type. This is runtime polymorphism in C++. We don't need to know the type at compile time. For example, you can store an int, a std::string, or a user-defined type inside any object. However, unlike optional and variant, which are type safe at compile time, any requires runtime checking. You can retrieve the stored value using std::any cast, but if the type does not match, it throws a std::bad any cast exception. While any is flexible, it comes with a performance overhead and a loss of type safety, so use it when you really need that flexibility. Here's a quick comparison table to help you remember the differences. Optional, used for a single value that might be present. Variant, a type-safe union that can hold one of several types. Any, a flexible container that can hold any type, but with less safety. Choosing the right one depends on your specific use case. Use optional when a value may or may not exist. Use variant for type-safe multiple options, and use any when the type is completely unknown or variable. Let's look at some real-world examples. Optional. Imagine querying a database for a user's profile picture. If the user does not have one, we return an empty optional std::string. Variant. Say you are building a configuration system. Your config file might contain a variety of values, an int for screen resolution, a bool for dark mode, and a std::string for the theme. Use variant to handle these different types safely. Any in a plugin system where different modules may pass values of completely different types. Any is perfect because it allows you to store and manipulate these values without prior knowledge of their types. Now it's your turn to implement what you have learned. Here are your tasks for today. Implement a function that returns an optional int for a user's age. It may be missing, so handle it carefully. Use variant to manage a set of configuration values. One can be an int, another a bool, and another a std::string. Create a simple logger that accepts any type using std::any. These hands-on tasks will help you internalize the concepts and practice using these tools in real code. Let's summarize what we have covered today. Optional, a wrapper for values that might not exist. Great for things like function results or optional data. Variant, a type-safe union perfect for cases where you know the set of possible types. Any, a flexible container for completely dynamic types, useful for things like plugin systems. Remember, choose the right tool for your situation. Don't overuse any when you can safely use optional or variant. Let's wrap up with a quick quiz to test your understanding. What happens if you try to access the value of an empty optional? A. It returns the default value. B. It throws a bad optional access exception. And C. It causes a compilation error. The correct answer is B. Always check if the optional contains a value before accessing it. Welcome to day 32 of our STL course. Today we are diving into custom comparators and functors in C++. These powerful tools allow us to control how data is ordered and processed in STL containers. By customizing your comparators, you will be able to define exactly how sorting, searching, and even prioritization are performed, giving us full flexibility when working with STL containers like set, map, and priority queue. Let's unlock the power of custom logic in our programs. Let's go over the learning objectives for today's lesson. By the end of this session, you will be able to understand what custom comparators are and why they are essential for specialized data sorting and searching. Learn how to define custom comparator logic using lambda functions and functors. Apply these comparators in STL containers and algorithms to achieve custom ordering. Finally, we will cover best practices to avoid common pitfalls when using custom comparators in your code. Let's get started. A custom comparator is simply a function or object that defines how two elements in a container should be compared. By default, STL containers like set and map use the less than operator to compare elements. However, when you need a different comparison logic, whether it's sorting in descending order, comparing by a specific attribute of an object, or creating a custom priority, you can provide your own comparator. Custom comparators are essential for tailoring the behavior of STL containers and algorithms to our needs. So why would you want to use a custom comparator? Well, consider this. You might have a list of people and you want to sort them by age, not by name. Or perhaps you want to sort numerical values based on their last digit instead of their actual value. Without custom comparators, achieving these would be challenging. Custom comparators allow us to define our own sorting rules, which is especially useful when working with associative containers like set, map, and priority queue. We can also integrate them into searching algorithms to control how comparisons are made. There are three main ways to define custom comparators in C++. Function pointers, the traditional approach where you create a function to compare two elements. This is a simple and clear method. Lambda functions, a modern and concise method where we define a comparator in place. It's great for small one-off logic. Functors, a function object that overloads the operator so we can call it just like a function. Functors are reusable, maintainable, and ideal for more complex comparison logic that needs state or customization. Each approach has its own strengths. We will explore these in more detail today, so we will be able to choose the right one for our needs. Let's start with the function pointer approach. Here we define a simple function called test that compares two integers and returns true if the first one is greater. This function is then passed as a comparator to the sort algorithm to sort a vector in descending order. While function pointers are a tried and true method, they can be a bit verbose and less flexible compared to other two methods, but they are great for simple one-time uses. Now let's look at lambda functions. Lambdas are quick inline functions and they allow us to define custom comparison logic without needing a separate function. In this example, we use a lambda to sort the vector based on the last digit of each number. The lambda expression is concise and works perfectly when you need a small, localized piece of comparison logic. This is a great choice when you don't want to clutter your code base with additional function names or when the logic is short-lived. Next, we have functors, which are objects that overload the function call operator. In this example, we define a compare by age functor that compares two person objects by their age. We then use this functor in a set, ensuring the elements are ordered by age. Functors are particularly useful when the comparison logic is more complex or needs to be reused multiple times. Unlike lambdas, functors can also maintain state, making them more flexible for complex use cases. Here's a great example of a lambda comparator with a priority queue. In this case, we are sorting pairs of integers where we prioritize the second element of the pair. By passing a lambda to the priority queue, we can customize the heap's behavior. This allows us to create a custom main heap where the elements are ordered according to a non-trivial comparison logic. This technique is particularly useful for scheduling tasks where tasks are prioritized based on their urgency and deadline. Which STL containers rely on custom comparators, primarily the associative containers, set and multiset. These containers use comparators to determine the order of elements, map and multimap. The keys in these containers are sorted based on a comparator. Priority queue. This container manages elements in a heap, and custom comparators can change the heap's ordering. On top of containers, many STL algorithms also use comparators. For example, sort, binary search, lower bound, and equal range. All rely on comparators when they are provided. Custom comparators enable fine-tuned control over these algorithms' behavior. While custom comparators are extremely useful, there are some common pitfalls to be aware of. Our comparator must enforce strict weak ordering. This means that if A is less than B is true, then B is less than A must always be false. If this isn't the case, the behavior of containers and algorithms can be unpredictable. Avoid capturing variables in lambdas when used as comparators in containers. This is because containers like set or map may store a copy of the comparator, which could lead to unexpected behavior. Const correctness is essential. Ensure that pointers are marked as const if they don't modify state. This allows them to be used correctly in containers that require const correctness. To wrap things up, here are some best practices. Use lambdas when your comparison logic is simple, short-lived, and does not need to be reused. Use functors for more complex or reusable comparison logic. Functors can also hold state, making them ideal for maintaining additional data during comparisons. Always ensure that your comparator is const correct if it does not modify any state. This is especially important when using functors with STL containers. Test your comparators thoroughly. It's easy to overlook edge cases, so always ensure that your comparators work correctly in all scenarios. Let's put our new knowledge to the test with some practice tasks. Sort a vector of pairs by their second element in descending order. Create a book struct and sort a set of books by publication year, then by title. Implement a custom main heap using priority queue to manage tasks based on priority and deadline. Now for your mini lab assignment, build a leaderboard system. Use a set or map with a custom comparator to rank players. Rank them first by score and then alphabetically by name. Implement functionality to insert and remove players and retrieve the top 5 players in order. Make sure to rank the scores in descending order. Before we finish, let's do a quick recap. Can you write custom comparators using lambdas and functors? Do you understand when and why to use function pointers, lambdas, and functors? Can you apply custom comparators to STL containers like set, map, and priority queue? Are you aware of the common pitfalls and best practices for comparators? If you can confidently answer yes to these questions, you are ready to tackle more complex STL problems with custom comparators. Thanks for joining today's lesson. Now that you understand custom comparators and functors, you can take full control over how data is ordered and processed in STL. If you have any questions, feel free to reach out. I will see you in the next class. Welcome to day 33 of our STL course. Today we are going to explore one of the most powerful combinations in algorithmic problem solving, STL and backtracking. Backtracking is an elegant technique used to explore all possibilities for solving problems with constraints. We will see how STL containers like vectors, sets, and maps can help us simplify and optimize these solutions. By the end of this session, you will be ready to apply these techniques to problems like generating subsets, finding permutations, solving n-queens, and even Sudoku puzzles. Let's dive in. Before we dive into backtracking, let's quickly refresh our understanding of recursion. Recursion is a method where a function calls itself to break down a problem into smaller subproblems. Every recursive solution has two critical parts: the base case, which stops the recursion, and the recursive case, which keeps breaking down the problem. Understanding recursion is crucial for solving problems with backtracking because it allows us to explore different states and systematically undo our decisions when they lead to dead ends. Backtracking is a powerful technique for solving problems that involve searching through all possible configurations. Rather than blindly trying each option, backtracking helps us prune the search space by abandoning paths that are invalid or unpromising. It's like navigating a maze and only moving down paths that could potentially lead to the exit. If you hit a dead end, you backtrack and try another path. This allows us to focus on more promising options without wasting time on fruitless paths. Backtracking is perfect for constraint-based problems like n-queens or Sudoku, where you need to satisfy certain conditions at each step. Now let's look at how STL containers come into play with backtracking. STL provides a wide range of containers that help us manage the state of our solution as we explore different paths. For example, vectors are great for dynamically building and removing elements as we generate subsets or permutations. Sets help us track states that we have already visited, ensuring that we don't waste time revisiting the same configuration. Maps, on the other hand, are helpful for memorization, where we store previously computed results to avoid redundant work, and we can even use stacks to simulate the recursive call stack in iterative backtracking algorithms. Subset generation is a classic backtracking problem. We want to generate all possible subsets of a given set of elements. To do this, we recursively decide whether to include or exclude each element from the current subset. Using STL vector makes this process efficient and straightforward because we can easily add or remove elements. With every recursive call, we explore one possible subset configuration, and if it's not valid or promising, we backtrack. The vector allows us to dynamically adjust our subset as we explore different paths. Here's the code for generating subsets using recursion and STL vector. Each recursive call will either include the current element or exclude it, and the results will be stored in the vector. Notice how easy it is to push and pop elements from the vector, which makes it a perfect fit for backtracking. This approach ensures that we explore all possible subsets efficiently. Another classic problem where backtracking shines is permutation generation. In this case, we need to generate all possible arrangements of a set of elements. We start by fixing one element in the current position and then recursively generate permutations for the remaining elements. STL vector helps us manage these arrangements in place, and backtracking ensures that once we explore one permutation, we revert any changes and explore other options. This is a great example of how STL can make recursive algorithms both simple and efficient. Here's a code snippet for generating permutations using STL vector. The key idea is to swap elements into the current position, recurse, and then swap back to undo the change. This process is repeated for all elements. STL's vector simplifies this task by providing dynamic array-like behavior, and the swap function is used to manage the element's position. Notice how this approach avoids the need for extra memory allocation, which makes the algorithm both time and space efficient. Now let's move to a more complex example, solving the n-queens problem using backtracking. In this problem, we need to place n-queens on an n-cross-n chessboard in such a way that no two queens threaten each other. We use a vector to track the positions of the queens on the board, and we use sets to track which columns and diagonals are already occupied. This allows us to quickly check if placing a queen at a particular position is valid. The power of STL lies in how it helps us manage the state of the solution efficiently and avoid redundant calculations. Here's a code for solving the n-queens problem using backtracking and STL containers. We maintain three sets, one for columns, one for the first diagonal, and one for the second diagonal. These sets allow us to efficiently check if a queen can be placed at any given position. After placing a queen, we recurse to the next row. If we reach a point where no valid position is found, we backtrack and try another column. STL makes managing the state and checking constraints much easier. Now it's your turn to practice. Try implementing recursive solutions for these problems on your own. Start with generating all subsets of a string. Once you are comfortable with that, move on to generating permutations, making sure to handle duplicates properly. For an additional challenge, try solving Sudoku using backtracking or implement a word search solver. These problems will really test your understanding of recursion and backtracking combined with STL. To summarize, today we have seen how STL containers like vector, set, and map can be used to simplify backtracking algorithms. These containers help manage the state, track constraints, and make the code cleaner and more efficient. Backtracking is a powerful technique for solving many types of constraint-based problems, and STL helps you implement these solutions quickly and easily. Next up, we will be diving into some advanced practice problems. This will challenge your skills in STL, recursion, and backtracking, and are perfect for preparing for coding interviews and competitive programming contests. Get ready to solve complex, real-world problems that combine multiple techniques in interesting ways. Welcome to day 34 of our STL course. Today we are diving into advanced practice problems designed to challenge and enhance your understanding of the standard template library. As you work through these real-world challenges, you will get the opportunity to apply your knowledge of STL containers, algorithms, and optimization techniques to solve complex problems. By the end of the day, you will feel more confident and ready to tackle any STL-based problem. Before we dive into the problems, let's quickly review the key learning objectives for today. By the end of this session, you will have learned how to solve complex problems using STL containers like vectors, maps, and DQs. You will also deepen your understanding of STL algorithms and how to use lambda functions and custom comparators to fine-tune your solutions. This day is all about practical application, so expect to walk away with the skills needed to tackle real-world problems efficiently. Now let's discuss an efficient problem-solving strategy for using STL. First, it's essential to understand the problem thoroughly. Identify the constraints and break the problem into smaller subproblems that can be tackled using STL containers and algorithms. Next, choose the right container, vectors for dynamic arrays, DQs for quick insertions or removals, or maps for key-value pairs, and of course use STL algorithms to streamline your code. Finally, always focus on optimizing your solution for both time and space complexity. By following this strategy, you will be able to approach any STL-based problem methodically and efficiently. Our first problem is sliding window maxima. Here we are given an array and a window size k, and our task is to find the maximum value within each sliding window of size k. This problem is often encountered in real-time monitoring systems, like tracking the highest stock price over a set period or monitoring CPU usage in a system. We can solve this problem efficiently by using a DQ to store the indices of array elements and ensure that the maximum element in the window is always accessible. The advantage of this approach is its n time complexity, which is far more efficient than brute forcing it with nested loops. Moving on to the frequency sort problems, where we are tasked with sorting a collection of elements based on their frequency of occurrence. The catch, in case of a tie in frequency, we need to sort the elements themselves. This problem is common in tasks like ranking or categorizing data, where we need to identify and prioritize the most common items. We can use an unordered map to count the frequency of each element and a priority queue or max heap to sort elements by their frequency. Custom comparators allow us to handle the tie breaking by sorting elements alphabetically or numerically. This gives us an efficient and customizable solution. Problem 3 challenges us to find the top k most frequent words from a list. This is a natural extension of the previous problem, but with the added complexity of only returning the top k elements. Think of it as identifying top trending keywords from a body of text. Again, we will use an unordered map to count word occurrences and a priority queue to efficiently retrieve the k most frequent words. We will also use a custom comparator to handle situations where multiple words share the same frequency, ensuring they are sorted alphabetically. This problem is very useful in text analysis, search engines, or social media sentiment analysis. Next, let's tackle the group anagrams problem. We are given a list of strings and our task is to group all the anagrams together. The key to solving this problem is recognizing that anagrams, when sorted, will have identical character sequence. By sorting each string and using the sorted string as a key in an unordered map, we can easily group all anagrams together. This approach is commonly applied in tasks like spell checking or deduplicating text data. It's an efficient solution that can handle large datasets with minimal computational overhead. Problem 5 asks us to sort string T based on the custom order provided in string S. This problem requires a custom comparator where the sorting order of T is determined by the sequence of characters in S. A priority queue can help us achieve this ordering, and we will need to create a mapping of each character's position in S. This type of sorting is often useful in scenarios like localized sorting, where elements must be ordered based on specific linguistic or cultural rules. In our bonus problem, we need to schedule tasks while respecting a cooldown period between executions of the same task. This problem is common in task scheduling systems like CPU scheduling or event-driven applications where tasks must be spaced out to avoid overload. We can solve this problem using a priority queue to select the next task to execute and an unordered map to keep track of the remaining cooldown time for each task. This approach ensures we handle tasks in the optimal order while respecting the cooldown requirements. Now let's talk about some useful debugging and optimization tips. First, prefer using unordered map over map when you don't need the elements to be ordered, as it offers faster access times. Avoid unnecessary copying or sorting, especially when working with large datasets, as this can lead to performance bottlenecks. When working with large data, take advantage of STL algorithms like copy if and remove if to simplify your code and reduce the need for manual loops. Lastly, always profile your code with large inputs to catch any performance issues early and fine-tune your solutions. Now it's your turn to put your skills to the test. Choose one of these exciting hands-on challenges. Implement an LRU cache using unordered map and list. Create a music playlist manager using STL containers, or build a leaderboard using set or map with custom rules. These challenges will help you apply all the concepts you have learned today and reinforce your ability to use STL effectively in real-world scenarios. As we wrap up day 34, remember that solving advanced problems with STL is all about applying the right tools and algorithms in the right way. STL provides powerful containers and algorithms that make it possible to solve complex problems efficiently and elegantly. Keep experimenting with new problems, focusing on both performance and readability, and continue challenging yourself to master STL. You are now ready to take on even more advanced problems, whether in coding competitions, interviews, or real world projects. Welcome to day 35 weekly assessment for the STL Mastery Series. Today we are taking a step back to assess your progress and solidify your understanding of the essential STL tools we have covered in week 5. This assessment will test your grasp on pair, tuple, bit set, optional, variant, and more. You will tackle multiple choice questions, code tracing challenges, and coding exercises to ensure you are ready for the final weeks ahead. Today's goals are simple but essential. We will evaluate your theoretical understanding of STL tools, ensuring you are comfortable with key concepts. You will put your practical coding skills to the test through coding challenges and problem-solving exercises. You will identify areas that need extra attention before we move into the final stages of the course. This is your opportunity to assess your strengths and pinpoint areas for further improvements. So let's dive into the assessment. Here's how we will structure today's assessment. Part A. The first part consists of 10 multiple choice questions that will test your understanding of STL concepts. Each question focuses on specific topics like bit sets, optional types, map, operations, and more. Part B. Next we will have 5 code tracing problems. This will ask you to analyze a piece of STL code and predict its behavior. It's your chance to demonstrate how well you understand STL containers and algorithms in action. Part C. In 3 coding challenges, you will apply your skills to real-world problems, solving them using STL tools like pair, tuple, map, and others. Part D. Finally, there's an optional mini project for extra credit. If you want to earn bonus points, this project will allow you to showcase your creativity and problem-solving skills with STL in a more complex scenario. Here are a few sample questions from part A to give you a sense of what to expect. What happens when you apply the XOR operator to two bit sets of the same size? How does optional differ from variant, and when would you use one over the other? If you wanted to store different types of data, how would you use tuple to make your data structures more efficient? These questions will test your ability to recall theoretical concepts and distinguish between related STL tools, so be sure to pay close attention to the details. Now let's move on to part B, which consists of code tracing problems. For example, you may be given a code snippet where you are asked to trace the output of a program that uses a vector of pairs and sorts it based on a custom comparator. This is an important skill. Being able to predict the behavior of STL algorithms and containers in real time will make you a more efficient programmer. The goal here is to evaluate how well you understand the flow of STL operations. In coding problem 1, you will write a function called filter event that processes a vector of integers. The function should return a vector of optional int where even numbers are wrapped in optional int and odd numbers are represented as null opt. This problem tests your understanding of optional and conditional handling. It's a great opportunity to solidify how optional values work and how you can conditionally wrap or skip certain values based on their content. Next, we have coding problem 2, which is all about grouping data. You will need to organize a set of student records containing roll number, name, and grade into a map based on their grades. The map will use char keys for the grade and store a vector of tuples for each student in that grade. This challenge tests your ability to manipulate map, tuple, and vector, and how to efficiently group and store data in STL containers. For coding problem 3, you will work with a bit set to simulate a basic 8-bit register. You will need to implement operations like set, reset, flip, and display the state of the register. This problem is a fantastic way to apply your understanding of bit set and bitwise operations. Working with bit sets is an efficient way to manage binary data, and this challenge will give you hands-on practice with manipulating bits at the lowest level. For the optional mini project, you will build an arithmetic evaluator using std::: function or functors. The evaluator should take an operator and two operands, then compute the result based on the operation. You can use a map char function to map each arithmetic operation to its corresponding function. This project is designed to push your limits by applying advanced STL features like function, map, and lambda expressions. If you complete this project, you will earn extra points and, more importantly, gain deeper insight into how powerful STL can be. Let's take a look at the scoring guide. In part A, MCQ is worth 20 points with 2 points per questions. In part B, coding tracing is worth 20 points with 4 points per problem. In part C, the coding problems are worth 45 points with 15 points per challenge. Part D is worth an additional 15 points for extra credit. Altogether, you can earn up to 100 points in this assessment. After you have completed the assessment, take some time to reflect. Which problems did you find easier or more challenging? Are there any areas where you struggled? This is a great opportunity to review any topics that you are not completely comfortable with before moving on. Remember, it's okay to revisit concepts that may need more practice. The more you understand STL, the better prepared you will be for the final project and beyond. Looking ahead, we are about to enter week 6. We will begin applying everything you have learned in real-world scenarios. We will work on our final project, participate in mock interviews, and prepare for our certification exam. This week is all about practical applications of STL in industry standard projects. Keep up the great work, and let's finish strong in the final stages of the course.